All right. Take all these off, I guess. Okay. So this lesson is the final lesson in our first unit. Or I guess it'd be more accurate to say it's the second last lesson, because the last lesson about intermolecular forces I've asked you guys to do independently. But today's lesson is a brief one, and it's an important one, though not one we're going to spend a lot of time on. Though you'll spend a lot of time talking about it in university. And the reason I really want to focus on it is you're also going to spend a lot of time talking about these concepts if you take biology throughout. These concepts are really, really important in the biological sciences. So today we're talking about polar bonds and polar molecules. And you should remember, of course, that a polar bond is a bond between a covalent bond between two atoms in which the electrons are not shared equally. And so today we're going to talk about how polar bonds give us polar molecules. And the first thing we want to point out is that if the bond isn't polar, the molecule can't be. So I want to draw the example of carbon disulphide. And if we were to, draw a Lewis diagram for this, we would put carbon in the center and sulfur around, because carbon has a lower electronegativity than sulfur. We would put a sigma bond between them. We would fill the surrounding octets. And we would count electrons, knowing that carbon should give us 4, and sulfur should give us 6 each, for a total of 12, for a total of 16. And if we look here, we'd go 2, 4, 6, 8, 10, 12, 14, 16. So we would see that we have to apply double bonds. All right, and quickly, we would know that we have 2 pi bonds here. So that carbon must be exhibiting Sp hybridization. And it must have a bond angle of 180 degrees, all that from yesterday. None of that really applies to today's lesson just yet, though we're going to talk about it, but I don't need to change the shape of this. It's drawn right. It should be a straight line, just like that. It is linear, because anything with Sp hybridization is linear. So now, to ask myself, is this molecule polar, which is what this lesson is all about? Does this molecule have partial charge? Is it polar, or is it nonpolar? Another way of asking it would be, from your intermolecular forces assignment, is this going to show dipole-dipole interactions, or will it only have London dispersion forces? And the quick way to tell is the first thing we need to look at is the bond polar? So here we have a bond between sulfur and carbon, and we have to look at the difference in electronegativity. Carbon has an electronegativity of 2.55, and sulfur has an electronegativity of 2.58. I'll put the little periodic table in here for you. So those numbers are. And if you look, I've already done the math, the difference in electronegativity here is only 0.03. And if you remember, we typically define as polar anything from 0.3 up to 1.7. You'll see some textbooks that say 0.5 to 1.7. You'll see others that say 0.5 to 1.5, but we'll work with this as a definition. So by any stretch of the imagination, this difference in electronegativity is really low. At just 0.03, we say that the difference in electronegativity isn't in this range, so it's not a polar bond. So the bond between sulfur and carbon isn't polar, and so the molecule on the whole can't be polar. And I hope that makes sense. So when we draw a diagram, we don't have to ask anything else. If we look at the difference in electronegativity and it's very, very low like this, we can say this is not polar, because the difference in electronegativity is too low. And I want to contrast that with a different compound. If we look here, we're going to look at hydrogen chloride, HCl. You may be tempted to say this is hydrochloric acid, but we're actually going to talk about it in its gaseous state here. how a different way that it can exist. So hydrogen chloride, and if we were going to draw a loose diagram for this, we would say that hydrogen is going to give us 1 electron, chlorine is going to give us 7 electrons for a total of 8. We would put them together with a sigma bond. We would look at the hydrogen. It already has a, oh, what am I doing? There we go. We would look at the surrounding atom, which we typically think of as the hydrogen here. We'd say it already has a complete octet. But because I only have 2 electrons and I need 8, we fill in the difference on chlorine. And now we have a stable molecule. So this is the Lewis diagram of hydrogen chloride. And here, if we look, the difference in electronegativity is equal to chlorine's 3.16 minus 2.2 for hydrogen. And if you do that math, you should see that the difference in electronegativity ends up being 0.94. Excuse me. Sorry. 0.96. So that electronegativity is big enough for the bond to be polar. And note, it's low enough that's not ionic. So there's not a transfer of electrons. It is polar. But this tells us that the bond is polar. And we show that over here by actually drawing a little arrow over top of this. And it's an arrow with a tail there and a tip here. And this arrow tells us that we have a dipole here. And the tip of the arrow is where the negative charge is. So we say this is where the slight negative charge is. And that symbol that looks kind of like a not quite finished 8 is a lowercase Greek delta. It just means partial. And the slight positive is on this end of the dipole. You don't need to draw these in the future. I'm just showing them here to show that's where the poles are. So quite simply, the electrons spend more time with chlorine. This side where the tip of the arrow is negative. And the other side where the tail of the arrow is, that's positive. And that arrow is how we show it. So up until now, we've always said that this is it. Either the difference in electronegativity is low, in which case it's not polar, or it's big enough that it is polar. What I want to show you today is that these dipoles can cancel each other out. And the first thing I want to look at is boron trichloride. So in this case, we have boron and 3 chlorines. Well, 3 chlorines gives us 21 electrons. In its valence. Excuse me. And then boron gives us 3 in its valence. Right? If you look here, it's in group 5. So it's got 3 electrons in its valence. And that gives us a total of 24 electrons. So when we go to draw this, we put a boron in the center because if we look, it has the lower electronegativity of the true. And around it, we put chlorine, just like that. Chlorine, chlorine, and chlorine. And we fill in the surrounding valences. And then we just count electrons. And we should have 24. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which is enough. So I don't need to add any electrons. But we know that boron needs 2 more to have a complete octet. So we're going to share a pair of electrons with the chlorine up here. And again, if we look really quickly, we'll say that this is Sp2 hybridization because we have 1 pi bond. And we said yesterday that everything that has Sp2 hybridization is 2-dimensional. In this case, we say it's that flat triangle. It's trigonal, planar, all right, and the bond angle is 120 degrees. And really quickly, we want to look and see that these bonds are polar, all right? The difference in electronegativity is 3.16 minus 2.04, and that, excuse me, works out to 1.12. And that is enough to give us a polar bond, which means that here, the electrons are always going to spend more time with chlorine. So in this bond, the electrons spend more time with chlorine. In this bond, the electrons spend more time with chlorine. And in this bond, the electrons spend more time with chlorine. And we're going to ignore the double bond, the pi bond, and I'll tell you about why at a future date. You don't need to worry about it. But what I want you to see is that these arrows actually work to cancel each other out. If we look at them, one tells us to go up here, the other to go down here, and the other to go down here in this direction. And you can imagine that if you were to follow these steps, if you walked forward, 5 steps, then turned 120 degrees to your left and walked 5 steps, and then turned 120 degrees to your left again and walked 5 steps, you would actually end up right back where you started. These 3 lines cancel each other out. So we say that even though it has 3 polar bonds, this whole thing is not polar, because the dipoles cancel each other out. All right, and that happens because they're symmetrical. All right, and so if we were to redraw this whole thing, but if we replaced one of those chlorines with something much closer to boron's electronegativity, say a hydrogen, we would end up with a different situation. So if I had boron bound now to hydrogen, chlorine, and chlorine, in this case, we would say that there's a dipole here and a dipole here, but no dipole here. And in this case, we would end up with these two adding together to give us an overall movement in this direction. And so we would say that this is polar. All right? Because the dipoles don't cancel. And the long and the short of that is, if all 3 of the bonds in this case are to the same thing, then they're going to cancel out. But if 2 of them are to the same thing and the third one is to something different, they don't cancel out. And this also, by the way, could just as easily have been a lone pair of electrons. And if it were a lone pair of electrons, these 2 dipoles would still not cancel out. So anything other than another chlorine will let these dipoles make the thing polar, as long as it's not symmetrical. And that's the rule. If the molecule is symmetrical, it cannot be polar. And I just want to quickly show you that that can be 2-dimensional, like we see here, but it can also be 3-dimensional. And I want to look at the example of methane. And this is one we've drawn a lot, so I'm just going to quickly draw it. But I'm going to draw it in that 3-dimensional shape that we're coming to understand. That we have hydrogen here and hydrogen here. And then we have one that kind of comes out towards us, like this, hydrogen there, and one that kind of fades into the background. Hydrogen back there. And I hope that drawing makes some kind of sense. Remember, this is that tripod shape we saw yesterday. And again, I want to show you that the difference in electronegativity is 1.22. All right, so this is sp3 hybridized, which means it's going to be 3D. Specifically, we call this a tetrahedron. Excuse me. So the bond angle is 109.5 degrees. And the difference in electronegativity is 1.22. So the bonds are polar. All right, and that means that for each one of these bonds, we have to draw a dipole. That means that there's a slight negative, oh, and we need to draw it in the right direction. So that means that there's a slight negative charge here, and that the electrons want to spend the time with the chlorine. There's a negative charge here, and there's a negative charge here, coming right at us. And there's a negative charge here, coming right at the chlorine too. So coming from all four directions. And I want to show again that those four dipoles coming at each other like this also serve to cancel each other out. And therefore, CH4 is nonpolar. And this is, again, because the whole thing is symmetrical, because all four bonds are made to the same thing. There's no lone pairs, there's no chlorine, there's no oxygen, there's no different thing here. All four of those bonds are the same. So even though each one of them is polar, because they're all the same, and because we know that hybrid orbitals always get as far away from each other as they can, the whole thing has to be nonpolar. Whereas if we were to replace just one of these with something else, if we put carbon in the middle and had it bond with all these things again, hydrogen, 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 but on top we put a chlorine, well, I hope you'd see that now, because chlorine is different, we get a dipole here again from hydrogen to carbon. And another, and another. These are all very slight, and they cancel each other out. But then to chlorine, we have a very large difference in electronegativity, just like that. And so that one dipole is enough to not worry about the other three, and this is polar. And we say simply, it's not symmetrical. Right? All of which is to say, what we want to check every time we look at one of these is, are the individual bonds polar? And then, is the molecule symmetrical or not symmetrical? All right? And the quickest way to look at that is if every single sigma bond, or every single hybrid orbital rather, is making a bond to the same thing, then it has to cancel out, whereas if the sigma bonds are made to different things, they don't cancel out. So that's all. Yeah, have a wonderful day.